We'll talk about some of the properties associated with the linear time invariant systems in both continuous time and discrete time domains. Uh, if you recall, the two important characteristics of such systems that we derived in both continuous and discrete time domain was that for any given input, xt or xk, be it an input discrete time sequence or a continuous time signal, the output is always given by the convolution sum. Okay, uh, it could be convolution sum for discrete time systems, okay, if they're going to handle the discrete time sequences or signals. And if it is a continuous time system, continuous time LTI system, the output is given by the convolution integral. Okay, so this YT is computed via convolution integral. And if you notice in both these convolutions, uh, impulse response is extremely important. Okay, impulse response helps in a complete characterization of such systems. Only we are talking of only LTI systems. Okay, so if it was for example for linear time varying systems, then you won't have this ht minus tau or hn minus k. Okay, this property is coming from time on we are invoking time invariance over here. Okay, so this discussion only holds to LTI system. Convolution is only valid for LTI systems, right? So you see, if for such systems, you know what is the impulse response, and then for any arbitrary input, xt, for example, the output is can be computed in terms of the given impulse response. Okay, so all you need to do is to flip the impulse response, and then time shift that, as we have seen in many examples before. The time shifted and the flipped version of the impulse response is all that you require to compute the output y of t for any arbitrary input xt, and the same goes for the discrete time domain as well. Okay, so you just need to flip the sequence, the impulse sequence, okay, time shifted, and then multiply it by the corresponding input samples, okay, add them over k and compute the output y of n. So in order to compute the output of such systems, you need the impulse response. Okay, for LTI systems, the impulse response is required. So now, if you recall previously, we have developed an extremely important representations of continuous time and discrete time LTI systems in terms of their unit impulse responses. So unit impulse responses are very important for LTI systems. They completely characterize the system and they help you in evaluating the output. Okay, so the output is evaluated in terms of impulse response. Now, in discrete time representation, it takes the form of the convolution sum. Okay, so this is the convolution sum. While in the continuous time counterpart, we have the convolution integral. Okay, now if you recall, we talked of how x of k or x of t can be expressed in terms of delayed pulses. All right. Now, if you limit the duration of a finite pulse to a very small interval, then this summation approaches to an integration for continuous time. So that was a natural transition. Okay, so you note that both integration and summation are they're also linear operators. Okay, and they tend to give convolution some of very interesting properties that we're going to look in detail in this video. So anyways, these are the convolution. This is the convolution integral, and this is the convolution sum for the discrete time domain and the continuous time domain. So LTI systems, they have a number of properties which is not possessed by the other systems. So beginning with the very special representations that they have in terms of convolution sum and integral, let's start with some of these properties. Okay, so the first one is that the convolution is commutative. What it means is that this is the basic property of convolution in both continuous time, discrete time domains. So it means that the commutative operation holds. You see, in both of these convolution integral and convolution summations, both the integration and summation operation are linear operators. Okay, so it can also be shown. Okay, I mean by linear operators I mean that if I tend to bring two inputs x1 and x2, then I can distribute the convolution operation over an addition operation. That means convolution is also distributive. Okay, owing to the linear operation of summation and integration. That's another thing that we can look upon, and we're going to discuss that also in detail. But by commutation, it means that the order in which you are computing the output y of n, for example, this is y of n, the order what is convolved with whom is not important, right? So for example, you can convolve x of n with h of n, or h of n convolved with x of n in that order. The order is not important, okay? So this summation, well, it is still equal to summation of xk multiplied by h of n minus k. What does it mean? It means you don't need to always flip and time shift your impulse sequence. You can also do the same operation with the input x, okay, and then you can multiply the samples of hk and sum it up over k. Okay, this summation is always over. It's also over k. So you either you flip and time shift x, the input, or you do the same for the impulse response. The result will be the same. The result will be the same. Okay, then multiply it with either hk or xk, and then sum it over the entire values of k. The result is going to be the same. It will be y of n. So the convolution operation is commutative, and the same goes for the in continuous time. The operation is again commutative. So you can always flip and time shift your input. Okay, and you can treat your impulse response as an input to the system. Okay, so over here, well, if you think of h tau as an input, okay, I mean, since the result will be the same, it's the same as doing x tau, the integrand. You change the integrand as x tau, ht minus tau. The result is the same as yt. Okay, that means what you're doing is you're changing the characteristics of the. I mean, you're interchanging the input and the impulse response of the system. So if you treat xt minus tau as the flipped and time shifted impulse as an impulse response, and you treat h tau as your input, well, the result is going to be the same, okay? Because the convolution operation is commutative. So these expressions, they can be verified in a very straightforward manner by means of substitution of variables in convolution sum and integral. Now, for example, okay, what we are doing over here is, you see, n is an integer, okay, in all these cases, and k is also an integer. K is an integer over here. So let's consider dummy variable r equal to n minus k. R is also an integer. So integer, a difference of one integer from another integer is always an integer. It's not a fraction. Okay, it's an integer. Then equivalently, you can write as you can make the k as the subject of formulation. You can write k from here. You see, you can write k as n minus r. K is also an integer. Okay. So if you bring this r over here, this becomes, okay, this becomes x of r. I mean, okay, let's do this over here for this summation. The result will be, I can have this as x of r. Okay, then about h, I can replace k. How I replace this? This becomes n minus r. Okay, this becomes n minus r. N minus r. Then you see that k, the limit is the summation is over k, which is varying from minus infinity to plus infinity. That means if you consider the relationship of k and r over here, since k is varying from minus infinity to plus infinity, or look from here as well, k varies from minus infinity. That means r variation of k from minus infinity to plus infinity implies r is also varying from minus infinity to plus infinity. That means the summation r, the summation is over r, can also written as minus infinity to plus infinity. And this r is a dummy variable. It's a dummy integer variable. So you can bring any other dummy variable. It could be hn minus m, x of m, and you can bring back k as well. Okay, it doesn't matter. I mean, so if you bring back k, you end up in this expression. Okay, so which means you are reversing the roles of you're reversing the impulse response with the input. Like, so you have over here x of r, hn minus r. Okay, so you have, if you bring back k instead of r, then it is x of k, hn minus k, right? This is commutation. Okay, this is commutative property of convolution basically. So like here, hn convolved with xn by definition is as such, and then for n minus k, you replace this by r over here, and then for k you substitute by n minus r. Summation r also varies over minus infinity plus infinity, and this means that either you can convolve hn with xn or xn with h of n. The result is going to be the same. Okay. This can also be shown for the continuous time operation, okay, because this what is convolved with whom is not important. Okay, so this is also x tau, ht minus, I mean, changing the integrand, changing which signal is to be flipped and time shifted and then is to multiply by the other is not important. So the order is not important. I mean, you can change this, the variables for continuous time. You can show the result is the same. So the convolution operation is always commutative. Okay. So okay, we have the same commutation operation for the convolution sum over here by changing of variables. So what this implies is that now with this substitution of variables, the roles of x of n and h of n are interchanged. Hence, the output of the LTI system with the input x of n and the unit impulse response h of n is identical to the output of an LTI system with input h of n and the unit impulse response x of n, right? So right here there was, for example, over here we are considering this as an impulse response. Over here we can consider h of k as an input. Okay, this was impulse response, so this is the input. I mean, which signal is what is not important because the order is not important. So input and the impulse response can be interchanged. So whichever you want to flip, you can flip and time shift either the input or the impulse sequence and multiply it by the other impulse response or the input signal. The result is going to be the same. Okay, the result is going to be the same. So therefore the convolution sum can be calculated by first reflecting and shifting the input and then multiplying the signals xn minus k and hk over k and finally summing the product values over k. So the result is going to be the same. Similarly, the convolution integral can be verified by changing the variables and the implication of the results in a continuous time are the same, which means that the output of LTI system with input xt and the unit impulse response ht are identical to the output of LTI system with input ht and the impulse response xt. Okay, so this happens by the virtue of commutative property of convolution, right? And you know that this is only valid for LTS. So we are discussing of LTS system where the convolution operation is valid. It's not valid for non-linear systems. It's not valid for non-time for time varying systems. Okay, it's just for the LTS systems that these properties hold. So thus the integral can be calculated by reflecting xt, multiplying the signal xt minus tau and h tau, and then integrating over the limits of tau minus infinity plus infinity in general. Okay, so this is for the commutative property. Now comes the distributive property, another important property that I was talking earlier. You see, since your summation and integration operation are linear operations, that means the distributive property is going to hold. That is, the convolution is distributive over additional operator. So another basic property of convolution is distributive property. Specifically, the convolution distributes over addition. So in the case of discrete time domain, suppose you have a system, okay, in which you are, for example, let's say, feeding your, you have two systems. Well, okay, let's construct this system over here. First LTI system has an impulse response H1n. Then there is another system which has an impulse response H2 of n. Okay, and we are going to apply the same input. These are connected, okay, and to this system you are going to apply x of n, right? So x of n is applied at the same time to both the systems to produce an outputs. Let's call them y1 and y2. Let's call them y1 and y2. So okay, over here I have y1, it's given by the convolution of xn h1. Then I have another output, call it y2 of n, which is given by x of n h2 of n, and if I add them up over here, let's have an addition operation. So this is an adder. It is adding two sequences, okay, and the output is y of n, which is a linear combination of y1n and y2n. Okay, so this is equal to y1n, y2n. Well, by the distributive property, you can see that either you can apply the input to these two systems which are connected in parallel simultaneously, or you can have a system such that the system has an effective impulse response. So let's call this HE effective, HE subscript double F as H1 plus H2. Okay, so I'm dropping this n, which is the discrete time index, but I mean the implication is the same. So well, what it means is you can have a system which has an equivalent impulse response of H1 plus H2, to which we are going to apply the same input x of n. The result is going to be the same. The result is going to be the same. It would be the output, same y of n, which is given as y1 y1n plus y12. Okay, this is by the virtue of distributive property of convolution, which again holds for the LTS systems only. Okay, and you see the convenience that is offered by the distributive property is that, okay, for example, what we're looking over here is, look, well, in terms of the summation operation, this can be written as h effective of k, which by which by this system is h1 and h2. Okay, and then you have this input, so you can flip this, time shift this by k, and then multiply it, sum it over k to produce an output y of n. So, well, what happens is over here is that you can write this summation as, well, as summation h1 k plus h2k. Okay, this I'm just expanding the h effective, that is the impulse response of a system, of a parallel connected system, or a system which has the impulse sequence that is the summation of 2. Okay, and then again xn minus k. So these two expressions are equivalent. These two expressions are equal. Okay, they are exactly identically equal. Then this, well, since summation operation is linear, you can produce two summations out of this. Okay, the first summation will consist of h1 of k x of n minus k, which is my first output. Okay, which is my first output y1, and then I'm going to add the second output. So then summation, again another summation over k, which has the impulse response h2k multiplied by x of n minus k. Okay, so you see I have formed two outputs, y1 and y2. Okay, so this is y1 and y2, the two outputs. So this is distribution. This is distribution. Okay, and it shows that a parallel connected interconnection of the system can be solved serially if you have a same system. Well, it's not exactly the same system, but the impulse response of the system, if the impulse response of the second system consists of h1 is h1 plus h2, the output is going to the same. Okay, so you don't need a parallel connection over here. These two configurations are producing the same output. Okay, so that means the two systems are identical. So because you see, if you write this as x convolved with h1 plus h2, the convolution is distributive over the addition operation. So x1 plus h, it can be either you add the two impulse responses, then convolve x of n, or convolve xn plus h1. Okay, convolve xn with h1 and then add it to another response xh2. This is going to produce the same output. So the output in either case will be y of n. Okay, this is y of n, and the same thing happens in continuous time domain. Again, the integration is a linear operation. So if you're going to write this for, you're going to solve this for the convolution integral, if you replace your summation by integration, again you will have two integrations. Okay, these two integrations will be over tau from minus infinity to plus infinity, and you will have y1t and y2t. So this is y1t, this is y2t. So convolution is distributive as well. All right. So you see in this figure 223, this is the interpretation of the distributive property of convolution for parallel interconnection of LTS systems. So what it says is distributive property has a useful interpretation in terms of system interconnections. So if you consider two continuous time LTS systems in parallel as indicated in 223a, the system shown in the block diagram with indicated unit impulse responses, these two systems are identical. The outputs yt over here, they are the same. Okay, so either you can have a parallel interconnect, or you can have a system which has an impulse response that is summation of 2. So integration is a linear operation. Okay, so you can say that, okay, h effective tau will be basically h1 of tau added to plus h2 of tau, right? and then you are going to convolve this with your input signal by basically the same time shifted and flipped version of your input signal to compute the output y of t. So it will be the same, that either you use this system to compute y of t, or use this system, in which case your output y of t is equal to y1 plus y2. Okay, because you see this integration is also going to produce two integrations, and it will be h1 of tau into x of t minus tau plus d tau. Okay, tau is your integration variable, plus ht h2 of tau into x of t minus tau. So there's no difference. Okay, so either you can sum this y1 and y2 to produce yt. So over here the situation is y1 plus y2. Again, you see this output is the same as y of t. Okay, this y of t. So it has a very important interpretation in terms of the interconnection of LTI systems. You can have equivalence, you can derive an equivalence of the systems. Okay, and in implementation of digital systems, you can save resources such as number of adders or delay elements, memory elements, requirements for the system interconnections by exploiting the properties of commutation, commutative and distributive properties of the systems. And you can, for example, these two systems in 223A and B, they'll have different digital resource allocations. The first system could be much slower as compared to the second system, which is which might save on the memory requirements or the digital hardware requirements like addition and multiplication. Okay, so although the output is the same, but the digital requirements are different. Okay, so if you write the hardware, it will be different. So these commutative and distributive properties, they have to be understood, okay, before you write the digital hardware of the system. Okay, now again, this is the interpretation of these two systems with having impulse response h1, h2. They have identical inputs and their outputs are added. So you've seen that y1t was basically, this y1t is your xt convolved with h1t, and this y2 is xt convolved with x2. So these two expressions, you add them up. So this is distributive property. Okay, so again 223 has the same output. So basically this is the distribution. Okay, and these two outputs are identical. Therefore, by the virtue of distributive property of convolution, a parallel combination of LTI systems can be replaced by a single LTI system whose unit impulse response is the sum of individual unit impulse responses in parallel combination. So the individual responses are y1 and y2. Okay. So also, as a consequence of both, if you consider both the commutative and distributive properties, what you can understand is that instead of having h1 and h2, you can replace the roles of the impulse response with the input. So you can have x1 and x2 over here as over here. Okay, you can interchange the nature of the input and the impulse response. The output is going to be the same. I mean, y of n is still going to hold. Okay, it will be the same. So it doesn't matter if the input and the impulse response is interchanged. The output is still going to consist of y1 plus y2 because of distributive property, and this y1 y2 gives you y of n. Okay, so there's no difference. The output is the same. So this is both due to commutative and the distributive properties. Again, this holds for the continuous time systems as well. This is y1 y2 added up, and we get y of t, right? So y of t is equal to y1 plus y2. Okay, so interchanging the roles of input and the impulse response has no consequence, as the output is the same due to the virtue of commutation. Okay, so which simply states that the response of an LTI system to the sum of two inputs must equal to the sum of responses to these signals individually. So you see, you have individual responses y1, y2. You add them up, you get the same output. Okay, so basically interchanging or interpreting them as an input, so x1 and x2 becoming input, or h1 h2 considering them as an impulse response, it has the same interpretation. The output is going to be the same. Okay, Okay, so this is 2.10 from your course text, Oppenheim Schaeffer second edition. So what it says is it exploits both the commutative and distributive properties to solve this example and bring some convenience in solving this example by using these two properties. So let y of n denote the convolution of the following two sequences. Now you see x of n over here consists of u of n and u minus n. That means x of n exists for all n. Okay, it exists over the entire time axis. H of n is u of n, which means this is u1 for n greater than or equal to 0. So you note that the sequence is x of n is non-zero along the entire time axis. This makes the direct evaluation of such convolution somewhat tedious. Okay, so instead we may use the distributive property to express y of n as a sum of the results of two simpler convolution problems. So what we do is we bifurcate this x of n into x1, which exists for n greater than or equal to 0, and then this is x2, which exists for n less than or equal to 0. Okay, x1 is this, x2 is defined as such. And then by exploiting the distributive property, y of n is still equal to x1 plus x2 convolved with hn. Okay, and that will produce your y1 plus y2. Now, if you recall, the example that we have considered before as well, in example 2.3, we have a similar sequence in which was of the case which had the form of a and un. Okay, a was I think less than 1. So if you consider over again, you substitute a for 1 over 2, you will have a similar result. Okay, for y1. We had this result before from example 2.3. If you've not seen this video, please check out the previous videos in the examples that we took for the convolution sum evaluations. So you can find the result in example 2.3. Similarly, for this for the sequence for which the samples are non-zero for n less than 0, this was example 2.5, and if you have those results, if you consider the results and add them up, you directly have y of n. So instead of doing direct convolution, you can exploit your distributive property and you just sum those previous results up, find y of n. Okay, so again, your y of n is xn plus x2, x1 and x2. We have bifurcated the original input into x1 and x2, and then you can have the two outputs, add them up, which are already there. So y1n was obtained from 2.3 with a equal to 1.2, and for y2, if you want to check how the evaluation is done, it's done in example 2.5. So we are just summing this up in figure 224. This is 224, and it shows xn and hn for example 2.10, and you can see this since x of n was there for all was present for all n, the y of n is also non-zero for all n. Okay, so y of n is also going to exist for the entire time axis. So I mean, this is the advantages of, you must understand the convolution has this important properties of commutative, being distributive, and you can exploit these two to make the convolution summation evaluation easy if these two properties are exploited over here. You will see next that I mean, this is easier than computing the entire sequence. If you consider the entire sequence x of n convolved with u of n, it becomes tedious. So distributive property comes to help us over here. Now you will see that in the upcoming video that this convolution is also associative. Okay, and it also offers some benefits in evaluating convolution integral as well as convolution summation. So exploiting these properties make the evaluation of such convolution integrals and summations much easier. Okay.